talk about photospheric imprints of coronal electric currents and their relevance for flares and CMEs. Currents are important because they are believed to be the mechanism by which energy is stored in the corona that is later released in flares and coronal mass ejections. So today I want to show some images of photospheric imprints of these coronal currents. These are signatures in the photosphere of currents flowing in the corona. I want to show some flare-related magnetic field changes, and these will show that photospheric currents either persist or intensify, which means that currents are not eliminated by the flares, so we have to account for how energy stored in currents decreases in flares, and we propose that that happens by, on average, shortening fields, which lowers their inductive energy. Finally, I want to talk about what happens before that shortening of fields, before flares. We believe that the coronal magnetic field actually inflates, which we call pre-flare coronal inflation. So in order to show these photospheric imprints of coronal currents, I need to decompose the photospheric vector magnetic field. I'm going to break the horizontal field into two components, a rotational component and an irrotational component. For the rotational component, we can define a stream function. If I take the curl of the rotational component from Ampere's law, I get the vertical current, and that gives me a Poisson equation to find the stream function if I want it. We're actually most interested in the irrotational part of the field, and the irrotational part of the horizontal field is the total horizontal field minus the rotational part of the field. It's whatever is left over after I subtract off that rotational part. Just to give you an idea of what this looks like for active region 10930, I took some data that was used by Shriver et al. In a study, some Hinode SOT-SP maps of the active region, and I broke the horizontal magnetic field there into rotational and irrotational parts. On the right, I'm showing the irrotational part with the red vectors, and the background grayscale shows a positive sunspot in white and the negative sunspot in black. In the left panel, we see the rotational part of the field, and you can see these whirls of the horizontal vectors, and the grayscale background is JZ. So clearly there are some important currents flowing in this, active region. So I've talked about the irrotational part and the rotational part. Now I want to talk about the non-potential irrotational part of the field. And in order to find that, I take the irrotational part of the field and I subtract off the horizontal field one gets when one does potential magnetic field extrapolation with the observed vertical field as a Neumann boundary condition. So if I take the irrotational part of the field and I subtract off the potential field, what's left with is the non-potential irrotational part of the field, the NPI part of the field. And to show you what that looks like, I've got the same active region before with the same grayscale of BZ before, but now we see that the non-potential irrotational part of the field points not as one would expect from positive to negative, but rather in the inverse orientation from negative toward positive. And this, I argue, is consistent with a coronal current, a large-scale current flowing horizontally in the corona, basically to the left in this image, and maybe a little bit toward the bottom of the page. And that's shown here by this green vector. And if you use your right-hand rule and put your thumb along that green vector, below it, your fingers will point in the same direction as the non-potential irrotational field. Above it, they will point in the opposite direction, basically from positive toward negative. But at the photosphere, the NPI field points opposite to the potential field, which points along the blue vector shown here. So it's a non-potential field. You can also see a similar structure in active region 11158. Again, here's a negative region, here's a positive region, and the field points from negative toward positive. The NPI field does. And that's consistent with a coronal current flowing to the left and toward the sort of the bottom of the frame in this active region. Again, you can use your right hand rule in order for your fingers of your right hand to point along here. Your thumb needs to be pointed to the left and down. So there's some coronal current there. That prior image was just before a flare. Just after the flare, we see that the BNPI is still present, so that structure remains intact. The flare did not eliminate that structure. We can look at the rotational component of the field, and this grayscale map shows where the rotational component is, the change in the rotational component, is in the same direction as the rotational component in white here. So the rotational component in this active region points along the polarity inversion line, which is shown here in yellow. And in this entire white region, the change in the rotational component of the field was along the pre-flare rotational component of the field. So the rotational component of the field intensified. And if you remember, that rotational component of the field from Ampere's law is related to the vertical current. So it's very clear that flares do not eliminate currents. Coronal currents persist. We then have to ask, well, if flares do not eliminate currents or substantially reduce them, then how do flares release energy? Well, if you recall that the self-inductance energy of a current carrying coil is proportional to the loop's self-inductance, the coil's self-inductance times the current it carries squared. And the self-inductance is given by the ratio of the flux induced in a loop due to the current through that loop. And so you can represent that energy as the enclosed flux times the current in the loop. This also holds, or some relationship holds, for the mutual inductance, which is the flux from other currents through a loop times the current in that loop. We propose that flares decrease inductive energy by shortening fields, because this self-inductance strongly depends, its dominant dependence is on the size of the coil. So if you make the current carrying system smaller scale or shorter, then its energy has decreased. And shrinking coronal fields accords with Hudson's flare implosion model. We suggest that prior to flares, there is a lengthening of coronal fields due to pre-flare coronal inflation, which I try to illustrate with these maps of twist. This is basically, this parameter alpha sub z is basically jz over bz. And I've got a map of this twist parameter weighted by bz squared from 4 hours before the flare and from 20 minutes before the flare. And you might be able to see that the PIL region narrows. This is also shown in this difference image here, where white is where unsigned twist has increased, black is where it has decreased, and white has moved inward toward the PIL. This would happen if there were a twisted flux rope emerging and its intersection with the photosphere were decreasing, or if flux cancellation were occurring. Both of these things would tend to inflate the pre-flare coronal field. With that, I will show the main points of my talk. Thank you very much.